Hello everyone. In this video we're going to take a look at composite functions, which comes up quite a lot in the VCAR course, but hopefully by the end of this you'll be able to have a good handle of it and be ready for those exams. A composite function is essentially just a mixture of two functions. So if we think of our everyday life, we know the word composite means when you mix things together. In primary school you have composite classes. When you are taught how to do area or volume, you have composite shapes, you have composite solids and those sort of things. And you have composite materials where things are mixed together to make a stronger material at the end. And so we come to composite functions and we already know the language behind it. How to apply it might be a bit different, but we know the language. So we have a mixture of functions where we take one function and we substitute it into the other function. Now the function that we take and we put into something, we take it and we put it into the other one, that's called the inner function. The outer function, or the other one, sorry, is called the outer function. So the one that stays as the general form is the outer function, whereas the one we put in is the inner function. Now the notation for it is f of g of x or g of f of x. That order is very, very important. The second one is always what is substituted into the first one, replacing the x values in the first one, which we'll get to examples in a minute. So f of g of x, you can write it shorthand as fog and goff like that, but remember the first and the second order is important. This one here, I'll highlight it for you. These ones here, those are the inner functions from earlier. And these ones here are your outer functions. Keep it consistent with our highlighting here for you. Now, it's all well and good to substitute equations into each other, and you can always substitute one equation into the other. There's a very rare case where you can't substitute it in. In fact, I can't think of any cases where you can't just substitute one thing into another. However, it does not mean it is valid. You might be able to substitute it in, but it may not exist. Some very clear cases of that are things like when we have a square root graph. If you end up with anything negative under a square root graph, it doesn't exist. If you have anything negative or zero in a logarithm, that doesn't exist. If you have zero in a denominator, that doesn't exist without asymptotes or anything. So just because you can substitute it in doesn't mean that it exists. So we've got to check the case for when it does and doesn't exist. And again, don't forget order is important. So for f of g, so fog, to exist, the range of g to the second one's range, the inner range, must be a subset of the outer's domain. So we'll keep our colouring going here. That f is the inner one, sorry, g is the inner one here. So the range of g must be a subset of the domain of f, the outer ones. The range of the inner must be a subset of the outer's domain. And that is important because remember, I'm taking g of x, the equation for g, and substituting it into f. Now the equation for g of x is a way of describing the y values. I have x values and it gives me y values. So g of x is a y value, hence the range. And it's getting substituted into f of x. Now remember, when you substitute into a function, you replace the f value, the x values, when you're substituting into a function. So we're taking the range of g and we're substituting into the domain for f. So that must work. Otherwise you do not have a composite function that exists. Again, order is important. The second one always, the range of the second must always match the domain of the first. If you do that and it works, then the final domain of the function is the domain of g. Because remember, here's our inner function again here. We've taken the y values of g and put them into f. That's what this statement is here. We're taking the y values of g, put them into f. That is only going to work based on the x values in this little one here. Because think about it, where do the y values of g come from? The x values of g, which is the domain. So the domain of g of x will be the domain of g. The domain of f of g is the domain of that second one. Okay, that's really important. When you're doing any kind of questions with composite functions, it is really useful to be able to know what the domain and range of each function is from the very start. So I suggest you set up a table like this. You do not have to, but I would always suggest to set up this table, and you can hopefully see much more readily the domains and ranges and how they might mix. So let's give it a go. I think I got four examples in total. The first three all tied together, and the last one's a little bit separate, a little bit different style. So in this question, we're given two functions. I'm telling you they both exist. Prove it. Okay. Well, first thing I need to remember is that if this one is to exist, then the range of G must be a subset of the domain of F. So I have to prove that somehow. And if this one's to exist, then the range of F must be a subset of the domain of G. So let's find out the domains and ranges and see if we can prove that these two things are true. So let's look at the domain of f of x. F of x is a quadratic. There is no restriction given. So quadratics, we know, have a a domain of all real values. Remember, they just look, this one looks like this, turns at -3. There is no restriction, there's no division by 0, there's no square roots of negatives, it's just all real values. Sorry, I shouldn't have removed that because we're going to need it for our range. The range of a quadratic, remember, unless it's restricted, is always based on its turning point. In this case, the positive quadratic, the turning point is 0, -3, which we can read directly from our graph here. It's in turning point form already. So I can see the range of my quadratic is from -3, including up to infinity. Let's have a look at the square root graph. So the square root graph, it has a domain of 4 to infinity. Sorry, -4 to infinity, I should say. Because remember, under a square root graph, the values under a square root must be positive or 0, must be greater than or equal to 0. So what we're going to do is we're going to solve the bit under the root sign for bigger than or equal to 0. So that gives you x is bigger than or equal to -4, which can be written as -4 to infinity. The range, well, the range, it's a square root graph. We're starting at -4, and the endpoint is based on a y value there, which we're not given in this case, so it must be 0. So the endpoint of this graph must be at -4, 0. That's where we're going to start our graph. And it's a positive square root graph, so it must be doing this. So it means our range is from 0 to infinity. That's our range and our domain. Let's now check and see if the range of one is subset of the other. So let's start with this first one. So the range of G. What is the range of G? Well, the range of G, you can see the range of G is 0 to infinity. Now, is that a subset of the domain of F? Well, the domain of F is all real values. So is that true? And certainly it is. I mean, if I draw a number line, 0 to infinity looks something like this, whereas all real values look something like this. And you can clearly see that this one does lie with that one down there. So if you're not sure, I recommend drawing some kind of number line. That really helps to see which one fits inside the other one. So in this case, this particular statement is true. So therefore, f of g exists, and we've proven that now. Now let's check this other one. I might have to just move this table to make a bit of room though. First I'll delete. Let's move that over here out the way so you can still see it, but I'll move these down. Okay, the range of f. Well, the range of f we know is -3 to infinity, including. is that a subset of the g, which is -4 to infinity? Well, the answer is yes, but let's do a quick check to see. If I have a number line, here's my number line. There's 0. -3 to infinity does this, and -4 to infinity does this. Now I need to make sure this one fits in that one. And you can see that it does. This entirely overlaps, so it works. So this works. Yes, it does. Therefore, g of f exists. So if you're doing an exam or something, you would need to show that this is true for these composite functions to exist. So the question might say something like, show that it exists. You can't, or if it says explain why it exists, you can't just use your textbook definition here. This is not true. If you write that, all the examiners or assessors, whoever might be doing it, is going to look at it and go, oh, great, they can spit out what the textbook says. You're going to need to show it, and the way you show it is by writing out this line, because it's true. Okay, they can at least say, oh, you've now considered the range of f and you've considered the domain of g. Yes, it's true. So make sure you include those things. Now we've proven it, let's find the rule and domain of the function. So the rule of f of g means I'm substituting f, so something g into f. So instead of f of x, I'm now going to have f of whatever g was. And g we can see was square root x plus 4. And remember, this notation means wherever I say x in the original equation, which remember f of x was x squared minus 3, wherever I say x, I'm going to replace it with square root x plus 4. Squared minus 3 at the end. Now square root squared just undoes the square root, so you're left with x plus 4 minus 3, which leaves you with x plus 1. So there's the rule for your function. But what is the domain? So there's our rule as required, but it also asks for the domain. Well, the domain, remember we said if it exists, the domain of f of g is just the domain of g. That was our rule from up the top. So the domain of g was -4 to infinity. So we're going to have to put here -4, comma, infinity. In fact, I should have put x before it, but I managed to miss that. Sorry, we should put x is an element of that, or you could have written x is bigger than or equal to -4. Either one would have been fine. Don't write both, just write one or the other one. But it said the rule and domain, so I've included the rule and I've included the domain. Let's do the other one. So find the rule and domain of the function g of f. So this time we're going to replace x with f. So we know g of x was equal to root x plus 4. So wherever I see this x value, I'm now going to replace it with x squared minus 3. Just if I had g of 1, I'd replace x with 1. But now I'm doing it with the whole function. So square root of, instead of x, I'm going to write x squared take 3. And that plus 4 still stays the end there. I should actually highlight this as we go so you can see it a bit more clearly. That's what we're doing. Nope, the highlight is not going to work for me. That's fine. You get the gist. And now we simplify it. -3 plus 4 is 1. And we get that for our rule. There is the rule for g of f. Now to write the domain out the end, remember to write the domain. The domain of g of f, it exists. So remember the domain of g of f now becomes the domain of f. And we said the domain of f in our table, which we already wrote, domain of f is all real values. So because we've already got our table written out, we know all our values that we need. So all real values gets written in here like that. Now, a different kind of example you might get is not so much prove it exists. It may not be so much write the rule it exists, but you might be given a question something like this. So let f of x equal x squared minus 4 and g of x equals square root x plus 3. Find the maximal domain for f of x so that g of f exists. Okay, so For g of f to exist, what must happen? Well, remember the range of f must be a subset of the domain of g. Now, what's the domain of g? The domain of g we know is -3 to infinity. We can see that. Again, your square root graph, so the bit under the square root must be greater than or equal to 0, and you can solve that. So it must be greater than or equal to -3. So that means this range must be greater than or equal to 3, but the problem is at the moment it's an unrestricted quadratic, so the range of f unrestricted is -4 to infinity. That is a problem because -4 to infinity is not a subset of -3 to infinity. -3 is a subset of 4, but that's not what we're asking. We're asking -4 to there. So this is the problem. So essentially what I need to do is I need to restrict this quadratic so that its range is -3 to infinity. So if I draw these two out, there's -3 to infinity. That's what I need. I'm at -4 to infinity. So I need to cut this section out. I got to get rid of all that. I don't want any of that. So the way I do that is by drawing a graph in my mind, or I can draw it here. It doesn't really matter. It'd be nice if my colors up here worked for me, but I'm having some issues up there. Technical issues. Let's have a look at the equation x squared minus 4. If I draw x squared minus 4, it's a quadratic looking like this. We've got -4 down there, but I need to restrict it so that it does not go below -3, because that's what I'm trying to tell. I'm trying to make sure it fits in this. So I'm going to draw a horizontal line here at -3. And I can see everything to the right of that cross is bigger than -3, and to the left of that one is bigger than -3. So essentially what I need to solve is f of x being bigger than or equal to -3. And we have to remember how to solve our inequalities for this. So I'm going to have x squared minus 4 is bigger than or equal to -3, which means that x squared has to be bigger than or equal to 1. Now I can't just say x is bigger than or equal to plus or minus 1. That's not how it works with quadratics. With linear equations that works nicely. Quadratics it does not. But the plus or minus 1 does form a very important part of the puzzle for us. So x squared and plus or minus 1 are important. Go back to the inequalities video for quadratics I've done, or hopefully I've done by this stage, to have a look at how to do it. But essentially this plus or minus 1 is really important. So I'm going to solve it and give me plus or minus 1 as a little aside. I should actually write a little bit further. Tap away over here. Now with a quadratic inequality, you have intervals instead of specific solutions. So what we end up with is either solution is going to be between 1 and -1, or it's going to be less than -1, less than or equal to, union with bigger than or equal to. Now on a number line, that looks a little bit like these options here. So x there, you're either going to have between those two values, or you're going to have outside those two values. Now hopefully just by looking at the graph we said we had to go on the outside of those 2 points. You'll be able to deduce which of these two options we're going to need. It's clearly the second one. But what we can do is use a bit of a test point. If I substitute x equals 0 into here, I'm going to substitute x equals 0 in and see what happens. So x equals 0, you get 0 squared, which is 0. So the question is 0 bigger than or equal to 1? And the answer is no, it is certainly not bigger than or equal to 1, which means that the interval that contains 0, this one, is invalid. So when I substituted 0 in, it didn't work. So it's completely invalid. So we don't want that one. So that means we're left with x is less than or equal to -1 union, I didn't need that comma, sorry, union x is bigger than or equal to 1. So why have we done this? Remember, we're trying to make sure we restricted your f of x so that the range was bigger than or equal to -3. That was what this step was here all about. We've now solved that, and by solving it, we've ended up with this set of values here. If I have that domain for f, this is f's domain, but this is the domain for f that allowed me to have a range of -3 to infinity, which then fit as the domain of G up the top. That was the point. We're trying to restrict f so that the range will then fit in a G, and we've just done that. So now we can conclude, remember, if the range of G, the range of f now fits into G, the range of the inner now fits into the outer, we conclude that the domain, I should go back to my more regular writing colour, therefore domain of G of f equals the domain of f, which we've just decided was x is less than or equal to -1 union x is bigger than or equal to 1. And that is composite functions. A couple of different kinds of questions you'll see. I hope that answers a few questions for you guys. Hopefully that was well enough explained. Any questions, do post them and we'll see how we go.